example down. We'll work it together, and the instructions say use elimination. So that's what we're going to try to do again. And then we'll have a couple of examples where we practice using substitution today. Okay. Yesterday we introduced this topic saying that, it's not any different at all from the technique that you guys learned with 2x2s. What we're going to do is we're going to pick a variable, try and get rid of it. We're just going to have to do that in a couple of ways. We're going to have to pick a couple of equations, eliminate, pick a couple of equations, eliminate, and then we'll break it down. Remember our goal, and I was hitting my 9th graders up with this yesterday, our goal in doing these problems is to take it from a 3x3 down to a 2x2, and then be able to take that 2x2 down to a 1x1, and then solve it out accordingly. Okay, so I don't care if I give you guys a 3x3 or a 4x4 or a 5x5. Your goal is to slowly and surely break it down from a larger system to a smaller, more manageable system. That's our goal. Okay, so I will be calling on Charlie Griffith. Charlie, pick me a couple of equations here. I don't care which two you pick. You can go ahead and pick whichever two. The first one and the second one. Okay. Now, I got to be honest with you. I don't really like how these equations are written up. They seem to be missing something, don't they? What are they missing in each case? What do you think, Tiago?
Well, yesterday, each equation had x, y, and z, and these only have.
Yeah, so this is how you fix that. If it's missing a y term, what do you think we could put in place? 0y. Very good. We could put in 0y, because adding 0, that's the additive identity, isn't it? We can add 0 whenever we want to. Hey, Alex, I'm going to add $0 to your bank account. That doesn't change anything. Okay, so I can add 0y whenever I want to. And in this second equation, I'm going to add 0x. And in the third equation, I'm going to add, looks like 0z. Now it looks much like what we had yesterday, where we had column, 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 column. We had an X column, Y column, Z column, and we were good to go. All right, and Charlie has picked for us. He has said, hey, let's focus on these first two equations. All right, so James, if we're focusing on those two first equations, which variable would you like to eliminate, James? All right, now I want you guys to think about this. If I'm going to eliminate the x's, I got to be able to reach this, so I'm going to drag this down a little bit. If I want to eliminate the x's, I got a 3 here and I got a 0 here. What could I multiply times 0 to make it 3? Nothing. So I don't want to try and eliminate the x's. What else could I try and eliminate, James? That boy. Much easier to eliminate the z's. What would I multiply, class, times that middle row then? I'd multiply everything by 2. And in fact, let's do that. Okay? So we'll come over here, and I don't want to kind of scuzz anything up, mess anything up. So what I'm going to do is I'm going to leave that first equation alone. 3x plus 0y minus 4z equals 0. And then the second equation, I'm going to times everything by 2. So I'm going to get 0x plus 6y plus 4z equals -6. All right, I'm going to tally everything up. We got 3 and 0, that makes 3x. We got 0 and 6, that makes 6y. The z's cancel out, and we got -6, okay? And Andrew, what do you notice that I might be able to do to that equation to make the numbers a little bit more, a little bit smaller, I guess I could say? How so? Like, what do you notice I could do to both sides to make it easier?
Divide by 3.
Yeah, let's divide everything by 3. Very good. 2y equals -2. All right, so this is interesting. I've taken, in blue, a 3x3 system now, and I have, by working with the two equations that Charlie suggested, I've brought it down to where I've got one equation now in terms of 2 variables. Nate, if I've got one equation in terms of 2 variables, what else do I need? In terms of those same 2 variables. Yeah, I'll say that again. If I've got one equation in terms of 2 variables, don't I need another equation in terms of 2 variables? What's our goal? Our goal is to bring it from a 3x3 down to a 2x2. All right. Now, from this original system, does anybody spot another equation that's already in terms of those 2 variables, x and y? What do you see there, Jack? Yeah, that last one. So we actually, this example is not a hard example because they have done the work for me in that respect. Okay, I now have two equations in terms of two variables. Because we picked a couple of equations and eliminated z, I found another equation where there's no z involved, and so we're gravy. Now, if this, truth be told, if this was an example like what we did yesterday, in there weren't all these zero spots, then what would we do to find our second equation? Yeah, we would do the exact same thing. We would just maybe pick the second and the third equation and eliminate z. Or maybe pick the first and the third equation and eliminate z. This one's a little bit easier because it already had an equation that had z eliminated from it. Okay, so what we've got here is we've got a 3x3 system in blue that has now been simplified down to a 2x2 system in orange. 2x plus 3y equals -5. All right, the first of those orange equations came from over here where we did our work. The second came from right there on the bottom where we were already given that equation. So our goal has been accomplished. We took it from a 3x3 down to a 2x2. Now we're free to do whatever we want. This is a problem just like last week. Okay, Tiago. Oh, gotcha. Thought you had a question. All right. Now, at this point, I would be comfortable letting you guys run with it. In fact, I would hope that you guys would go off and say, yeah, I can solve that either by using substitution or elimination. Okay, and we can find, regardless which way we do it, we find like y equals this, or we find like x equals that. So once we get it down from a 2x2 to a 1x1, where we say like, I know what one variable equals, then we can go through and we can start plugging and chugging and find out all the other variables. When you get one number, when you get one answer, that's when it's solid and you're ready to roll. Okay. Now, let me encourage you guys to use a lot of paper on these problems. Have lots of space in which to work. One of the ninth graders yesterday, his complaint was, I feel like this takes up a lot of space. And I'm like, yeah, if you're doing it right, it does. Okay. Don't be afraid to use some paper. Don't try and cram everything into just one little spot right there. All right. Luke, what method did you use for the orange one? Have you gotten rolling on this at all? Elimination. What variable did you want to eliminate? The x's. All right, so I'm assuming you multiply the top by -2, right? All right, so let's see here. Let's come on down here and we'll make a new equation. So -2x, -4y, and what do we multiply by -2 times -2 makes +4. All right, so I'll just scratch through that. X is eliminate, -y equals -1, also known as y equals +1. Fabulous. So we took it from a 3x3 in blue down to a 2x2 in orange, and then we just solved, and we got our one number. Now, Joey, what do you want to do with that y equals 1? Yeah, and we can plug it back in wherever we want to. I kind of think it'd probably be simple to plug it in over here. 2 times 1 equals -2. Let's subtract 2 from both sides. We get x equals -4. And then I could take that, and why don't we come over here and we'll maybe just plug it into this first equation. If x is -4, 3 times -4 minus 4z equals 0. So that's -12. Add 12 to both sides. Divide by -4. What do we get? Z equals -3. Fabulous. All right, and Reed, how do I write my answer up for this one? Yeah, very good. An ordered triple. So -4, 1, whoops, I was leaning on the keyboard, pardon me. -4, 1, -3. And visually speaking, do you guys remember what the graph of a linear equation in 3 variables looks like? What does it look like? What shape does it look like? It's not an airplane. It's a plane. And if you got 3 equations of 3 variables, you're going to have 3 planes. And we said, graphically speaking, then, what y'all just found was this point of intersection right there. You just found the point that was on all 3 of those planes, right? And it's got 3 coordinates because it's an ordered triple in 3 dimensions. All right. 4, -3. This is a very similar answer to the last question. Huh. Go figure. All right, that's using elimination. And I got to be honest with you. For a 2x2 system, I'm happy to use elimination. With a 3x3 system, I actually prefer using substitution. So this next couple of examples that we look at, let's use substitution. Okay, you got any questions on example 2, by the way? All right, here's our next example. Okay. Now go ahead and write this down. You'll notice everything's already lined up nice and neat in the columns for us. Now with substitution, it works similarly, again, to how we learned in the 2x2 systems. You pick a variable and you get it by itself. Ben, I'm gonna let you pick. What variable would you like to get by itself and in which equation? You just pick one equation, pick one variable from that equation and get it by itself. You said z in the first equation. I like that. There's actually 3 options that I think would provide you with the least amount of work. You know what I mean? I would consider getting z by itself, or y by itself, or y by itself. And Will Edwards is going to tell everybody why.
Coefficient of 1.
That's right. And therefore, I will not have to do any division. I won't have to deal with fractions. Okay? So very good. Ben has chosen for us, what'd you say again, Ben? Z in the first equation? All right, let's do it. Let's get z by itself. So I think I'll add z to both sides and subtract 2 from both sides. Z equals 3x plus y minus 2. Can you follow along with that? You get z by itself. Now, this is substitution, okay? So I'm sick. I'm going to call in a sub. Sub's going to take my place. Here's the little twist. Here's the little deuce, little curveball we're breaking off, okay? Nate, can you hit a curveball? We'll work on that. Nate, when's the last time you played baseball? 3 years ago? That's all right. They weren't throwing curveballs back then, so that's okay. Or at least they shouldn't have been. Last time I hit, like, consistently for my baseball team was 8th grade. When I got into high school, it started getting harder and harder and harder to hit. And so I became a PO. What's a PO? A pitcher only. And so the sadness of my life was that I never got to hit again. Unless it was like BP, and they were like, all right, pitchers, y'all get in there, get 1 round of BP. And then it was like I was at the World Series, man. It's awesome. It's great. But I digress. Here's what we're going to do. We're going to take this expression, 3x plus y minus 2. Okay, that's the same thing as z. We're going to plug that in for z, not just in one of the other 2 equations, but in both of the other 2 equations, right? Grove, what's our goal for this type of thing? We got a 3x3 system. What are we trying to do? All right, more generally speaking. Jake, what's our goal? We've got a 3x3 system, and what are we trying to do? We're trying to bring it down to a 2x2 system, okay? So if I look right here and I say, hey, there's a z and there's a z, and I can rewrite that second equation, 2x minus 3y minus 2, not 2 times z, but 2 times 3x plus y minus 2, right? Now that's an equation in terms of how many variables? It's now in terms of 2 variables. And then if I come over here in blue, I'll do the third one in blue, right? And I say, all right, well, this one is 4x minus y minus 3, not 3z, but 3 times what? 3x plus y minus 2. Now, I've got that 2x2 system. I got 2 equations in terms of 2 variables. All right? I just need to clean them up a little bit. Can you guys clean them up a little bit for me? Like using distributive property, combining some like terms. Right? Here we go. I'll help you on the blue one. So we're going to distribute. What are we distributing there? What? -3. All right, good. So that's -9, x, -3, y, and +6 equals 0. Quentin, help me clean that up. Combine some like terms for me, brother. Nope, the blue one, the one that we're just now working on. Fabulous. All right, what else? I like it. I like it. Keep it coming. Keep it coming. I'm shooting for standard form, by the way. I like standard form. So I got an X, I got a Y, I got an equal sign. Can we move that 6 over? Subtract 6 from both sides, and you're there. All right, very good. Now, what do you guys notice is maybe in common with all three of those terms? They're all negative. So why don't I divide everything by -1 and get 5x plus 4y equals 6. To me, I'm a positive person. I like things to be positive. So there we go. That's one equation now in terms of two variables. Can I lean on you guys? I'll give you 60 seconds to do the green one. 60 seconds. On your mark and set, go. You guys simplify out the green one now, and we'll have our 2x2 system. We'll have it nice and neat and cleaned up and ready to roll. And as I silently work this one out, I'm going to encourage you guys to pay attention to the little details, right? The devil's in the details, as they say. Pay attention to the small steps, like multiplying by a negative. Don't screw up the easy steps, the little steps, okay? There's a lot of them we don't want to mess up. So take your time and do it right. All right, do you guys concur? You had actually 75 seconds. You're welcome. Y'all concur with what I got for 4x and 5y and 3? All right, let's put those two together, and let's see if we can solve that little system there. So we got 4x plus 5y equals 3, and we got 5x plus 4y equals 6. So this is where we're working right here. Now, I don't know about you, but I think I'm going to do elimination here. Substitution would involve fractions, and I really don't feel like dealing with fractions. So which variable do y'all want to eliminate? I don't care. Call it out. X is going. All right. So the least common multiple between 4 and 5 is 20. So to get the x's to have 20, I need to multiply the first one by 5 and the second one by, and I'm going to say -4. So that one of them can be positive, one of them can be negative, because I like to do it that way. 20x. Don't mess up the small details, right? 5 times 5 is 25y. 15. -4 is going to be -20x. I like that. -16y and -24. X's are gone. Ooh, what's that going to be? 9y. Y'all double check my arithmetic. And then -9. So y equals -1. Are you getting more comfortable doing this process? Are you getting more comfortable with elimination?
Seemed harder than substitution. Like the entire thing.
Mm-hmm.
Seemed like it took longer.
It can feel that way. And what I would encourage you guys to do is practice both techniques. Practice substitution, practice elimination. And then whichever one, to use Tiago's words, whichever one feels harder, that's the one that we want to practice more of. Okay, so like we might be good at substitution, and we might want to spend a little bit more time practicing the other one, practicing elimination, or vice versa. Okay, because you want to be proficient at both of them, because there are some contexts in which one is easier than the other. Okay, now once I get y equals -1, I can come over here and plug it in wherever I'd like. 5x plus 4 times y equals 6. Solve for x. So we get 10, x equals 2. X equals 2. And then once we've got both of those, that's that linchpin. Everything's just going to trickle down, fall into place now. We got x equals 2. We got y equals -1. So let's come up here and let's plug it into orange. X is 2. y is -1. So what is that? 6 minus 1 minus 2. 6 minus 1 minus 2 is 3. And how do I write my answer up, class? An ordered triple. Just like this. We talked yesterday. What's a neat way for me to go ahead and check my work to make sure that I'm doing it right? I'm sorry, I didn't catch it. Alex, what'd you say? Okay, yeah, true that. We can plug it back in. Now, that would take a while. I'm thinking more like technologically savvy there. James? Do what? Yeah. Just like go to Google and find yourself a system solver or get yourself like a little calculator. The TI-36X Pro is a good example. It's like an $18 calculator. It'll do a lot of neat stuff that you guys can make use of. But heck, you can go to like Wolfram Alpha or Mathway or whatever. They've got system solvers, and that's a great way to check your work, okay, after you've done it to make sure that you didn't make any kind of careless mistakes. You know what I'm saying? All right, questions on example 3. Questions on substitution.
I have a question. Does it matter, like if you put the X, the Y, the Z, like in the ordered pair or the ordered triple thing, like what order you put them in?
Absolutely. Okay, great question. Always when we talk about ordered pairs, it's always X, Y. When we talk about ordered triples, it's always X, Y, Z. Alphabetically ordered. When we're in the context of just a system that's being solved out. Okay. Now it's going to be a completely different answer to Lewis's question when I jump down here and I've got like a word problem application of this. This will be our last example for today. And in this case, we're not going to put our answer in an ordered pair because context is not talking about some graph in the X, Y, Z, coordinate space. It's in the context of some community college selling tickets to their theater program. So we wouldn't write up our answers in an ordered triple in that case. All right. Now, in the textbook, I don't know if you guys follow along in the textbook, there's a nice little recap of how this process works. We're not going to spend time writing that down right now, but it's pretty much a summary of what I've taught you yesterday and today. Okay, so as you're reading through in your textbook, or if you're going back through and you're saying, oh, wait, what were those steps again? You can find them step by step right there in the textbook. This last example right here is a good sort of wrap up for our lesson today, because what it's going to do is it's going to require us not only to know the process of substitution or elimination, but also be able to apply it to our little 5-step word problem solving method, right? You guys remember your 5 steps? Figure out what the problem's asking, assign a variable, write an equation, solve an equation, answer the question. And in steps 2 and 3 will be a little bit different because instead of assigning a variable, here we're going to assign how many variables? 3 variables, or if we were in Germany, this many. In equation solving, the step 3, instead of solve the equation, it's going to be solve the system of 3 equations that we came up with. Okay. Now, let's see if we can get to it. When you guys are taking a test, like let's say you're in the ACT or the PSAT or whatever standardized test you're taking, you don't want to always read every word of every problem. And for me, that kind of bothers me. I've got a little OCD in that I like to just make sure I got all my bases covered. But really, if you're trying to be efficient with time, figure out what the problem's asking. I always tell students, jump to the end of the problem. Read the last sentence. Okay? And it says, how many of each type did the department sell? So I know in this problem, there's somebody selling something, and there's several different kinds of things that they're selling. And that makes the problem already take on a rate times quantity equals total type scenario. So in the back of my mind, very, very rapidly, I'm thinking this is like going to the grocery store. I pick how many of these items do I pick? How much does each of those items cost? And then I do that here, and I do that here, and I tally it all up at the end. Okay. Now, step 2, figure out what the variables need to be. Assign my variables. I'm going to say, look, there's adult tickets, there's student tickets, and there's child tickets. So I'm going to say let A equal the number of adult tickets. I'm going to say let S equal the number of student tickets. And what do you think? I'm going to let C equal the number of child tickets. All right. That's declaring the variables. That step might seem pesky to you. It might be like, gosh, coach, I don't feel like doing that. But I guarantee you that you'll get the problem You'll get a clearer result, and you'll be able to communicate that result easier if you've declared your variables. If you just say, well, x, y, z, blah, 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 and you get to the end of the problem and you're like, okay, x equals 2, y equals 7, and z equals 43, and then you got to figure out what does each of those stand for again? What are they asking me for? Go ahead and declare the variables right off the bat. Now, there's 3 variables, so I need to be able to come up with what, Joey? 3 daggum equations. Okay, let's read the problem and see if we can come up with each of them. I'm going to highlight the info that's going to tell us each equation, all right? So they sold 250 total tickets. George, write me that equation. It's going to use all 3 of our variables. A plus S plus C equals 250. Very good. That's my first equation. That's the easiest equation to come up with. That's just quantities. That's like, okay, well, how many tickets did they sell altogether? Well, A plus S plus C gets that job done nicely. Okay, so we use the 250. Our second equation is going to involve the price of each kind of ticket and the total amount of money that they earned. Okay, Jake, you want to take a stab at that one? You said 10S? $2,825. Fabulous. That's good old rate times quantity equals total. Okay, that's the grocery store principle. If I go to the grocery store and I buy 15 of these items, or excuse me, I buy A of these items and there's 15 bucks a piece. I buy S of these items and it's 10 bucks a piece. I buy C of these items and they're 8 bucks a piece. Then we're going to multiply, add, tally it all up. All right. Here's my last equation, and I bet you guys have already got this one taken care of. Right? The number of student tickets, S, is, what does is mean? Equals twice the number of adult tickets. Alex, what's that expression? Nope. What's twice the number of adult tickets? Twice something means do what? Multiply by 2. And how many adult tickets are there? Nope. Read right here. There's A adult tickets. So we want 2A. So S equals 2A. All right. So the whole idea, and I'll use Alex as an example, it's real easy if I've declared my variables and I say, wait a minute, how many adult tickets were there? Oh, yeah, I wrote it up. A equals the number of adult tickets. So we got S equals 2A. All right. Now, Mossy, what technique do you think is going to lend itself nicely to solve this system out? Substitution. We currently have a 3x3 system. Look at that top equation. I put it up there because I was just doing a direct translation underneath. But look at what we could do. Everywhere I see an S, I could plug in a 2A. All right, and I'll change colors here. In orange, you're going to have A plus 2A, not S. Substituting in place of that, 250. And then over here in green, we got 15A plus 10, not 10S, 10 times 2A, plus 8C equals 28, 25. All right, so now we've got 2 equations in terms of 2 variables, and I just need to clean it up a little bit. Can I go ahead and lean on you guys to do that for me? Y'all clean it up a little bit. Over there in the orange one, combine a couple like terms. Put it in standard form. All right, Luke, read off what I'm going to have when I clean it up. 3A plus C equals 250. Very good. Okay. Alex, you got the green one done yet? Read it off, Bubba.
35A plus 8.
Fabulous. That's now our 2x2 system. And you could solve that system using elimination or substitution, whatever floats your boat. Okay, let's go ahead and use elimination just because I kind of like that. Here, let's pull this down here. Can we just multiply the bottom one by 8? Okay. 8 times 3 is what? 24, and then 8. 8 times 250 is 2,000, right? And use my eraser. Let's make them all negative. So negative and negative and negative. Now we cancel out the C's. Oh golly, what is that? 11A and 825. Anybody done that division already? Alpha dogs. Nobody? Dagnabbit. I think it's 75. If I'm remembering correctly. Somebody check me on that. Joe, does that look good to you? All right. Now, if A equals 75, what do I do with that? Plug it back in. Over here in orange, we had, what was that? 3A. So 3 times 75 plus C equals 250. What is 3 times 75? $1.50. So that's going to end up being C equals 100. Right? Actually, 375 and 3 times 75 isn't $1.50. It's 225. Pardon me. So what do we get? Just 25. Yeah, my bad. I was thinking 2 times 75. So we got C is 25, A is 75. Now look, we could use some common sense right there, right? Or we could use one of those equations. If S equals 2A, then S is going to be 150. All right. Or we could just say, well, you know what? How many tickets were there altogether? There's 250 tickets altogether, and if A was 75 and C was 25, that's 100 altogether, so there must be 150 left over. And the way that we would answer this, and to go back to Lewis's question, would I put this in an ordered triple? No. I would just say, hey, there's 75 adult tickets, there's 150 student tickets, and there's 25 child tickets. And I'd answer it accordingly. You spell it out, take your time, write it out as you need. Okay. Very, very good lesson. Guys, that's an Algebra 2 lesson that we just learned. A lot of Algebra 1 classes that you guys take or that you guys encounter probably wouldn't go through and talk about solving 3x3 systems, and especially not in word problems. So kudos. That's some good hard work y'all done the last 2 days. That's wrapping up chapter 4 for us, okay? So I won't see you guys until Thursday. We'll start chapter 5 on Thursday. In the meantime, look on Teams. I've got a couple of assignments. There's one that's ACT practice, and then on Delta Math, you got a little practice assignment for this stuff as well. Y'all skedaddle on out of here. Live Jesus in our hearts. All right, boys. Thank y'all so much for a good class. You guys online, y'all take care.